saya Tingkilia, lulusan Bangkit 2021. Saat ini saya bekerja sebagai external code reviewer di Decoding Indonesia.
Saya Adi, lulusan Bangkit 2021. Saat ini saya bekerja sebagai Data Science Fellow di Jakarta AI Research.
Saya Vincent, lulusan Bangkit 2021. Sekarang saya bekerja sebagai Data Scientist di Bisa AI.
Halo, saya Dharma, salah satu lulusan Bangkit tahun 2021. Saat ini saya bekerja sebagai external code reviewer di Decoding.
Halo, saya Alia, lulusan Bangkit 2021. Saat ini saya bekerja sebagai Culture Engagement Analyst Intern di CMB Niaga.
Halo teman-teman semua, saya Harisno, alumni Bangkit program 2021. Saat ini saya menjabat sebagai CEO dari Jagawana. Dan juga saya bekerja sebagai Data Science di AI Tracking Working Group, sebuah tim riset dari Universitas Gadjah Mada.
Halo, saya Tirsa, lulusan Bangkit 2021. Saat ini, saya bekerja sebagai mobile dan cloud developer di Nongsa Digital Park, Batam.
Hai, saya Timotius, lulusan program Bangkit 2021. Saat ini, saya berperan sebagai co-founder dan software engineer di Bacara, salah satu top 15 capstone project Bangkit 2021 yang menerima pendanaan inkubasi dari Dikti dan Google.
Berkat Bangkit, saya dan tim telah membuat Jagawana, sebuah startup yang berfokus pada pencegahan penebangan ilegal yang mendapatkan pendanaan dari proses inkubasi Bangkit.
Terima kasih Bangkit, kesempatan belajar selama 6 bulan yang saya peroleh berhasil mengantarkan saya menjadi lulusan dengan predikat distinction di Bangkit 2021.
Bersama tim, saya bisa memberikan dampak di bidang kesehatan dengan membuat aplikasi deteksi dini penyakit demensia yang sudah tersedia di Play Store.
Sekarang saya siap memberikan dampak di bidang kelautan Indonesia dengan machine learning, dengan menjadi bagian dari tim pengembangan AI untuk terumbu karang bersama BRIN dan juga LIPI.
Saya telah berhasil tersertifikasi sebagai Google Associate Android Developer dan siap memberikan kontribusi terbaik di bidang teknologi untuk Indonesia dan dunia.
Terima kasih Bangkit, sekarang saya resmi menjadi Certified TensorFlow Developer.
Sekarang, saya menjadi talenta digital dengan kemampuan unggul di bidang cloud computing dan siap memberikan dampak positif pada Indonesia.
Bersama tim, saya bisa menciptakan sebuah produk aplikasi penerjemah bahasa isyarat Indonesia ke dalam bentuk teks dan suara secara langsung.
Terima kasih Bangkit.
Hello, good morning everyone across Indonesia. Let the journey begin. That's our beautiful tagline for Bangkit Academy. Welcome here in the non-mandatory session. Today we will talk about a lot, especially about convolutional neural network. And yeah, you've been shown that beautiful videos. A lot of my friends have been there. Timothy, Tinkilia, they're just beautiful and wonderful talent. And as well, all of you too, more than 3,000 students now have been almost join us in the chat as well. Don't forget to bring some crowd in the chat as well. And I think I should introduce myself as well after them. Hello, I'm Iga Narendra Pramawijaya, and you can call me Iga. And today I will be the moderator for our guest interview session. And today we will have Vincent Tatan joining us. So, well, I'm a Bangkit graduate myself, and Vincent Tatan is also, he's not a Bangkit graduate, but he, has been an instructor in Bangkit Academy for about 2 years now, 2021 and 2022 as well. Well, if you don't know, but Vincent Tatan is currently in United States, so it's a little bit dark behind him. And he's also a technical writer in Medium, talking a lot about AI and machine learning. And now he is a senior machine learning engineer and analyst in Google. But before, he has been to the data and software architecture engineer in Visa, data scientist intern in Lazada, and business intelligence intern in Visa. Hello, we have Vincent Tatan joining us from United States. Good evening, Vincent.
Hello, good evening, everyone, and good evening to you too, Iga, or good morning to you, Iga.
Yes, it's good morning here in Indonesia. Like, how is it in the United States? Like,
it's very cold
to get
here.
warmer?
No, it's still very cold.
Still very cold.
Yeah, I need to wear jacket whenever I go outside. So
Yeah, but you do really look good in batik. I do really encourage you to wear batik inside the Google headquarters there.
yeah, they all like it.
Oh, they all like it. Oh, yeah, it seems great to see like Indonesian Googlers to wear like their pride shirt, which is batik. How are you like tonight? Like, I know it's been like a really rough week for you inside Google and the security and analytics. So how's life?
Wow, life has been quite busy because I actually just relocated to US like a couple of like 1 month ago. So I'm still considered like not a resident here. So I haven't got my like kitas yet or like KTP. I still haven't got that yet. So I'm still like illegal here per se.
So yeah, before we move on to the material, what really encouraged you, Kak, to contribute to Bangkit again in 2022?
Yeah, I actually been there as an instructor since like 2020 when Bangkit first came into Indonesia. And at that point of time, there were only hundreds of students and they focused on machine learning. But now we see a lot of other tracks like, like Android development and Google Cloud development. And now there are 3,000 plus students that actually come here. So as an Indonesian, I feel very proud. Ya, dan juga saya bangga banget gitu ya. And I think that it's going to be a movement, right? Each one of you will become the future leader, future CEO, and future maybe like managers, right, in technology that leads Indonesia to the next step. And I think by contributing to here is like trying to plant the seed, right, in the ladang, right, in the field that I think is going to be panen soon, right? So we are going to harvest all of these efforts, and you guys are the seed. So really, really happy to be here.
Beautiful. Talking about seeds, we're about to also seeds, but now it's a neural network. Next, Kak Vincent will talk us a lot in convolutional neural network. Now, Kak Vincent, the stage is yours.
Thank you so much, Ika. All right. Hi, everyone. So I'm going to talk about intro to CNN. So this CNN is not going to be the news CNN, like the USA news, but it's going to be convolutional neural network. And this is by me. I'm as a Google machine learning engineer. So before we move on, right, let me introduce myself because kalau tak kenal maka tak sayang. Jadi harus kenal dulu ya, baru bisa sayang. So for me, I'm doing machine learning engineer at Trust and Safety Google. So these are like medium, right, where I document my work and regarding some tips and tricks, career advice. And there's also like LinkedIn where you can come and communicate with me, right? And there's also Data Podcast if you want to know more about my journey until I reach into Google. And hopefully all of this will be useful to you. And a bit of disclaimer, right? Just to make sure that there's no like miscommunication in the future, that this article and this presentation is purely made by my own initiatives and also is supported by Google. So in no way it is driven by any other agenda, right? So I'm not going to promote much about trust and safety. I'm not going to promote much about some confidential stuff in my company. Okay. So what do I do at Google, right? To summarize it, it's like to prevent phishing at scale with data analytics and machine learning, right? And if you don't know what phishing is, basically it's website bodong, di mana you see this kind of like, for example, like Facebook. But if you take a look at the URLs, which is the address that this website has, it's definitely not Facebook, right? It's San Agustin Turismo, which is like definitely Facebook phishing. And of course, this is a very, very complex. In fact, you'll see a bunch of like this kind of phishings where you talk about like Amazon, Apple, Netflix, and many other more. And what we do against all of these like website bodong is that we give you these red interstitial warnings that make sure that you do not accept, or maybe you do not access all of these websites. And of course, we package all of these inside machine learning pipelines which includes image, text, and graph. And if you take a look into it, the image part is the one that I highlight in a box, right? Which is what we are going to talk about today, right? How we are going to use image in order to run a neural network and, of course, predict something. So this is a little bit about an article regarding what I'm going to present today. I actually document the technical stuff inside Understanding CNN on Medium. So feel free to take a look into it. You can just like Google my name, Vincent Tatan, and then I put Understanding CNN, and you will just you will find it at the very first search. And we do also have like Collab Demonstration here. So for today's presentation, I'm not going to go through the Collab. I'm just going to take some snippets of the codes just to make sure that we have the time to cover all of this. Right. And of course, you might be thinking what's for today's agenda. So this is today's agenda, right? So we are going to talk about machine learning in image recognitions. What does it mean to take a look into images and then predict from it? And second is that we're going to talk about the technical stuff, CNN, which stands for like many different kinds of things, but you might want to think about these three important concepts, which are convolution, Relu, and max pooling. After principles behind CNN, I will prompt like 15 minutes Q&A plus break so that you can make a toilet break or whatever that you want to do and make sure that you can stay refreshed by the end of the day. And of course, I'm going to start with CNN stacks, fully connected layer. I'm going to talk about avoid overfitting with these like CNNs and neural networks, right? And finally, I'm going to talk about transfer learning and discussion. So I'm going to time myself with all of this will be like 1 hour, right? Excluding the Q&A. So it'll be like 1 hour and 15 minutes until we go into like the second Q&A, which altogether will take 2 hours. So make sure you get your coffee before this, right? And feel free to just like prompt me on a chat saying that if I speak too fast or maybe I speak in Singaporean accent or maybe like other accents that you might not really understand, feel free to let me know. Jadi langsung bicarain aja gitu ya kalau misalnya Inggris saya kurang bagus. Alright, so with that in mind, let's jump into the very first one. Let's put our excitement into learning what is machine learning in image recognitions. Okay. And of course, image recognition is hard, right? For example, after you Google, let's say, cat in the Google image, this might be cats and this might not be cats, right? All of these are not all of these are cats, right? So for example, you see that there are like cats at the top, but then at the bottom, you see that it's actually referring to the cats as a Broadway show, right? Which is a theater show, right? And even you take a look into like these pictures of like humanoid cats, and you take a look at this, which is like, I'm not sure what it is, but it seems to be a commercial. It might not be cats, right? So how do you know which one are legitimate cats? And of course, in traditional programming, what we do normally is that we take a look into the features. For example, we know a cat in this image has sharp ears or maybe like black color, right? And from that, we can do like color histogram. We can do like many different kind of like cut the lattices, right? And then take a look at how the colors like interact with each other, the spectrum, right? And in order to like code that, oh, all cats have black colors and sharp ears, right? So that's how you normally code in traditional programming. But of course, this might not be necessarily powerful, right? Because let's say that there is a cat wannabe, right? All of a sudden, the black colors and sharp ears, even though it fits the criteria, we know for sure that these are not cats. So what do? Is that you might want to add more features. For example, can we take a look into the nose? Can we take a look into the feet, right? Can we take a look into the eyes? And if you combine this with many different kinds of cats, many different kinds of animals, let's say like Siamese cats, and we also have like Egyptian cats, all of these will be very, very stressful, and you will have a headache. So what does it mean, right? We need an automatic way to determine critical features to identify cats or other objects, right? So you need to have more features apart from black color and sharp ears, and you want to have an efficient way for machines to learn all these features, right? So in one conclusion, in one sentence, we can summarize it as following. We need a way to determine the features scalably. End of questions, right? And that's why we want to talk about CNN, right? So what is exactly CNN? So CNN stands for Convolutional Neural Network, and you might take a look that there's a complex sequences there regarding convolution, subsamplings, and whatsoever. So I'm going to go through these layers, but there are three main components that you might want to think about, which is convolutions, Relu activations, and max pooling. So some of those are crucial in the current like CNN's infrastructures, but of course, some of these can be interchangeable, right? You can change it. For example, you can change activations to sigmoid, or you can change max pooling into average pooling, whatsoever, right? So I'm going to go through all these concepts one by one, and hopefully all of this will be clear. So these are the intuitions of convolutional network, and I'm going to start it with a picture, right? So what do you see? Do you see young lady or old grandma or both, right? What do you see here? Okay, I'm going to just give a little bit of pause so that you can think about it. Okay, since I couldn't see your chat, I'm just going to like I'm just going to say that, hey, this is old grandma to me, right? And the reasons why is that you can take a look that this is a grandma, right? With the this is the eyes and these are the choker, right? Or if you take a look at the ladies, then you know that this becomes an ear, and and grandma it becomes a mouth. In ladies, it becomes a choker, right? So there is a story behind this painting, right? Whether like you recognize this as an old grandma or young lady, and the reasons is because that from Edward Boring, it puts the painting of my wife and my mother-in-law, and it's supposed to be a visual illusion, right? Where the figure seems to morph from young lady to old woman, right? And there are actually a little bit of joke here, is that the features that you see are the one that you classify, and it comes from your behaviors, right? So for example, for older generations like me, I usually will look into this as an old grandma because let's say the cartoons, it's become usually for all cartoons like Popeye or like Tintin, then you know like the eyes are very, very small, right? It's very different from, for example, nowadays where you see the eyes are very big, so it's less likely for you to recognize the box on top as an eye, right? And it can be also because of the strolling, right? So because of strolling, for example, like you always like stroll up and down, you will see that the top box will come first, right? So it is more likely for you to become an ear rather than an eye, right? So just like by looking into these recognitions between like this image and what it represents in your mind, you know that you are relying on two things, right? For example, you know that it's an old lady or young lady from the data, right? The strokes of the paintings. And the second thing is the prior knowledge. For example, like your scrolling habits will determine whether this is a lady or old lady, or maybe your understanding of faces, such as what I mentioned to you in anime, usually have like big eyes. Current cartoons usually follow animes, or maybe the old cartoons usually follow Tintin and Popeye, which have like very small eyes, and you will more likely recognize it differently. And these two things, right, the data and the prior knowledge, will definitely determine what the machines recognize. And usually when you talk about the prior knowledge, it is mentioned as features in machine learning point of view. So let me just go through with it. For example, with the data, with the strokes, the machines will recognize this as a pixel, right, rather than the strokes of the painting. It will say, okay, let's say that the grayscales will be one, and the white color will be 0, right? So what happens is that it will have like this data where you see that 1 is labeled as black and 0 is labeled as white, right? And then it just keeps going on until by the end of the day, you notice there's a certain curve here, right? So there's a curvy shape. Whereas for the box below, you notice that there is a sort of a line kind of sequence, right? So it becomes a choker in your mind by combining all of this. So this is how the machines will take a look into the pixels. It doesn't take a look into the strokes, but it will just say, okay, 1 is black, 0 is white, or if they're like 256, then it will be a gradations, right? In RGB, for example, red, green, blue. So how does machines use data in order to find a certain feature? Well, a very simple way and very simple terms is convolutions. But what is convolution exactly? So convolutions is not something that's very, very machine learning. It's not something that just come up and becomes a hype. But a convolution actually is in everywhere, even before machine learning becomes popular. For example, in Instagram, you know that there is a filter, right? For example, you can emboss it, or you can do a grayscale. Whenever you take a selfie, you can make it a little bit artistic. All of these, the so-called filter, actually use a concept that's called convolutions. So for example, in this image here, this talks about edge detections. And what you see here is that you see an image, which is the input, and you see that there is a kernel, right? There's a kernel. Kernel is just a ND matrix, right? In this case, it's a 2D matrix, right? And this kernel has a certain value. So the idea is that by using convolutions, you can take this input and take this kernel, combine them to create this output. And if you see this output, you know that it emphasizes horizontal edges, right? Which is sort of like what the kernel is looking into. For example, like you see the horizontal edges here. Right, there you go. But how does it really work? Well, to know how it works, let's take a look into a very simple convolutions example, which is 1D. So for example, there's a question here. You have this n elements. So for example, there are 6 index in 1D element here. And I have a question. Which order of the element where I see there's a change from 1 to 0? All right, get the question, right? And of course, the answer is this, right? You know that it changes here. So you need to take a look that the index is 3, right? Or if you start with 1, the index is 4. So at the index 3, it changes from 1 to 0. But how do we get this input to become this output that you know the change from 1 to 0? Well, by using convolutions. So again, I'll put this as an input, right? 1, 1, 1, 1, 0, 0. And then the kernel, which is 1 minus 1. So this kernel I just specify on my own. So it's just like arbitrary numbers that you can put, right? And what you do is that you do dot operations within a certain window. So for example, I use the kernel at the right, and then which is 2 by 1. And then after that, I highlight the same dimensions, which is 2 by 1 here, right? And after that, I do dot operations. So what it means is that you have like two elements list here, for example. So basically, one is a 0 element, and the other one is 0 element. So 1 times 1 plus 1 minus 1 equals to 0. So I do dot operations from these two lists, right? Which I highlight. And after that, I will basically slide the window, right, from this 0 to 1 element to 1 to 2 element, right? So basically, I do another dot operations. So 1 times 1, which is the element 0 times element 0 in the other list, plus 1 times minus 1, right, which is 0. And I can do it again, and again, and again, right? That by the end of the day, during the fourth element, which is this one, you notice that something changed. That 1 times 1, it becomes 1, and 0 times minus 1, it still becomes 1, right? And then after that, 0 times 1 plus 0 times minus 1, it becomes 0 again. And the end result is this, right? So this is the magic of convolutions, right? You just create a kernel and then you just slide it. That's how it works. And of course, just now it was only a 1D. In 2Ds, it's even more powerful, right? So for example, you have the inverted V shape here, or like more than sign, right? And after that, you have these inputs in pixels. And I also have a kernel in pixels. So this kernel resembles like X, right? Or a number 5 in a dice. And what you do with this is that you use it to slide it, right? From the 0 element, you slide it to the right, you slide it, and then you keep storing the dot product values, right? To becomes like 1 to something like this, right? Which is I dot K, right? And what you see is basically an vertical lines detections, right? Because it accentuates where the verticals are. So for example, you know, like V, there's a like solve at the vertical at the right side, right? So you see that number 4 is actually highlighting where the verticals are, because this is where it resonates to the kernel. So I here is the input, K is the kernel, and I dot K is the feature map, right? So it's a map where you store a certain feature, right? Where it represents feature, right? So there you go, right? Data and K will be like prior knowledge that the machine learning have, for example, and IK will be the feature map. So we can actually do all of this even in RGB, right? So for example, in RGB, we just keep like convolutions and then slide it, right? And you will have like 3 different feature maps for you to combine on, right? So this is reproducible even in RGB. Okay. So I hope the convolutions is really clear. Basically, you just like create a kernel, which is your prior knowledge, right? And after that, you use the kernel in order to accentuate what is important based on your prior knowledge, right? The second thing is Relu, right? So Relu is actually a very common and popular activation functions for you to use in neural network, right? And in CNN, usually we use Relu as well. But if you take a look at the right, you see that there's StunH, logistic, soft sign, Relu, and soft plus, right? There are so many different kinds of types. But normally we use Relu a lot, and the reasons is because that first of all, it's very simple, right? So you can take a look that everything below 0 is 0, everything below 0 is the input itself, right? So if you take a look at the function here, it's just maybe 1 line or 2 lines of code. And the second thing why Relu is important is that it is still a non-linear, right? So it introduces complexity that you want to capture, right? So it captures these kind of complexities where by the end of the day, that it's not only just like 0 or linear, but it's also like something like a curve, right? When you put it into the neural network. And finally, of course, it sort of like mimics our biological functions. For example, like when we pinch our arms, we feel pain, but when we just touch our arm, we don't feel pain at all, right? And when you start putting a threshold to pinch your arm, right, until like you put pressure, at some point it becomes pain. And when you put more pressures, the pain becomes larger and larger. So I think really works because it mimics our body and it mimics how we sense pain, right? So this is really cool. And neural networks actually use a lot of inspirations from how our brain works. The second thing is max pooling. The third thing is max pooling. So max pooling is very simple. Is that let's say that you have this feature map, you are trying to reduce the feature map. So for example, in this case, we can split it into 4 segments. And each of the segments, we can pick what is the max, right? So for example, from the red segment, you pick 6, which is the max. From the green segment, you pick 8. From the yellow segment, you pick 3. From the blue segment, you pick 4, right? And based on these like 4 different categories, you are able to get a smaller feature map, right? And it works. It works just like how our brain works, right? Because there are 3 advantages to it. The first one is that you are reducing the size. So for example, from 4 times 4 to becomes 2 times 2, that's easily like 75% reductions. The second thing is that it overemphasizes what is important. For example, here, you just take the max. And of course, it also reduces and de-emphasize of what's not important. So you just leave out all of those that's not important. For example, 1 is below than 6, so you don't care about it. You just want to take what is the max. If you don't understand what I just talked about, I have this one analogy. Try to remember the coolest car that you have seen, right? For example, like a red Ferrari. Or maybe for girls, try to imagine the best dress that you have thought about, right? And think about it, right? Think about those dress and those cars. And let me ask you a question, right? Do you still remember whether the driver is wearing a sunglass, for example? Or do you still remember whether the one that wears a dress has freckles or has pimples? Well, probably you're like, no, I don't remember about that, right? Because in your mind, you will think about how cool the car is. Oh, the car is red color. You know where the logo is. You know all the kind of details, including what the tires look like, right? You know all the details. But if I ask you about something that's not important to you, for example, who are the drivers, you're like, nah, I don't know about it, right? So this is what max pooling does, right? The max pooling emphasizes what's important. In this case, is the car or the dress, and it de-emphasizes what's not important. For example, it's a driver, right? So in a way, it reduces the cognition load, right, in our brain. So we also use max pooling. Jadi teman-teman, belajar biologi itu sama dengan belajar convolutional neural network. Yeah. So just a recap, we have like convolutions where you just slide the window, right? And after that, find features, feature maps. And the second one is Relu activation functions, where you're trying to introduce nonlinearity to make sure that your neural network can grasp and capture complexity. And finally, max pooling, right? So basically, you emphasize what's important, you de-emphasize what's not important. Okay. Basically, I want to start like maybe like 15 minutes break and Q&A here. Iga, could you help facilitate?
Sure. Beautiful. Okay. As long as we are digging into the basics of CNN, we have lots of questions inside of the chat box. So I will address them one by one, and they are like, yeah, beautiful questions. I mean, like, not a kind of stupid questions. Okay. Move on. First question comes from Havis. Hello, Kak. How often to use CNN-based model in real-world cases? And in your opinion, is CNN better than other neural networks available? Hello, Kak, I think you're still on mute.
Okay, sorry.
Okay. Go ahead.
Yeah, I think that's a very great question, Hafiz. Jadi, how often that CNN is used in real world case? And the answer to that is a lot, right? But of course, different CNN has different like structures, right? Actually, there are a lot of research in image recognition alone, especially when you use it into like the current terms like meta, right? For example, like metaverse, right? We use like those kind of detections a lot, or even like in NLPs, right? So you can actually use convolutional in, for example, in words related natural language processing, right? And if CNN better than neural networks, of course, it would depend, right? All the all the questions about like better or worse is always like depends, right? Well, CNN, the big benefits compared to like just a vanilla artificial neural network, right? For example, if you don't know artificial neural network, it's just like, like you have a bunch of neurons, and after that you connect neurons within different layers, and then like you use activation functions, and by the end of the day, you come up with a verdict, right? And if you don't know why we need to use convolutions with that, it's because that there are some advantages that convolutions have. And one of the advantages involved in images, right? Because think about images, right? For images, let's say that image of a dog. You don't care whether the dog is at the foreground, background, up, left, and right, and down of the picture, right? You just care that, okay, I see a dog, right? And CNN works really well because it uses a window to just find whether the feature is there or not, right? So what it means is that it's space invariant, right? Whereas artificial neural network, basically, it will have like completely different functions. If the dog is left, if the dog is right, it's completely different functions. So CNN actually works a lot better than images compared to average neural network. And the second thing also is like efficiency, because artificial neural network is not space invariant, so it just needs to calculate everything, right? And it needs to be like overly complex. But for CNN, it does not, because it just cares about feature maps. And basically, you just pass along feature maps along the layers, and you can always like reduce feature maps with max pooling. So I'm going to show to you about how CNN works, and maybe it will be clearer how it's better than ANN in images.
Okay.
Yep.
Yeah, beautiful answer, in my opinion, because it's not really like going to, it's good or it's not. Yeah, it's really, real world cases depends. And also another interesting question from Laba, before we move on to like deeper in knowledge in CNN, how much mathematics that we need to be able to understand to use the convolutional neural network or any other methods outside of the mathematics?
Yeah.
This is a burning question, Kak.
Thank you so much. Yeah. Honestly, I'm not a mathematics guy. I'm just a hacker, right? I just love to just build a solutions. But yeah, it's very simple put is that to use CNN, you actually don't need a bunch of mathematics. You just need to understand the concepts, and you just need to, usually it's just trial and error, right? But of course, if you want to be an expert in CNN, for example, like if you want to understand how complex that your CNN needs to be, let's say with a hyperparameter such as the number of layers, how many number of layers that you need to put to identify, let's say, two images, two labels, right? Cats or dogs, for example, compared to all IKEA furnitures, right? Obviously, the complexities would need to be very different, right? The more labels you have, the more complexity you need, right? So if that's the case, for you to estimate which, like what kind of models and what are the inners behind the models that needs to process a certain goal, then you probably need to do a simple statistics and mathematics to look into it. But the mathematics behind neural networks is actually very simple, right? Which is basically you sum up all the neurons within one layer, right? So if you know like summations in mathematics, which is a sigma sign, that's basically what you use a lot in neural networks. And if you know that, like for example, how a certain perceptron work, so perceptron is like a very all unique unit of like neural network, right? Usually we call it neuron, but before that we have something called perceptrons, right? So multi-layer perceptrons. So if that's the case, it's very simple equations. Basically, you just follow like, okay, linear y equals mx plus b, and then y, there's a threshold within y. So more than threshold. So if it's more than threshold, then you put some value into it. Below than threshold, then you put like zero to it, right? For example. So that's the mathematics that you need to know with CNN actually on neural networks. But of course, the most important thing is to understand the concepts and understanding how you can get value from CNN. Yeah. So.
Okay. So, wow. It's a little bit fascinating that the CNN concept that we are using right now is, let's say, has been there for since 1945, like in the invention of perceptron. So another following up question from Fajar: why CNN? Since it's so simple, it's more powerful with data with high dimensionality, such as images and 3-layer images, like the RGB thing that you mentioned. Why it's so powerful when it's so simple in the first place?
Yep. Thank you so much, Iga, and thanks so much, Fajar, for the questions. Yeah, this is a very understanding, very interesting concept, right? That CNN is simple yet powerful, right? And the idea is very simple. I actually talk about like just now, like CNN is space invariant. Is that you use the concepts of like how you scroll through a certain image with a kernel, right? So it's like you're wearing glasses, right? And then you look into a certain part of the image, and then you find, you find what's important to you, right? So I think CNN is powerful is because that it actually mimics more of our mental structures of like how we process informations. So for example, when you read Eptanas, or when you do Eptanas, usually you just skim through, right? You don't read like word by word. You just say, okay, this is what's important. Okay, these are the equations, right? These are the concept. I need to factorize it, or especially when you take like Bahasa Indonesia, right? Usually you just take a look into like what are the keywords, right?
You can the story. Let's
Yeah,
be honest.
it's like a long story. Oh, I still remember kayak when I take Eptanas, right? Yeah. So CNN is actually using that like skimming through approach, which is very different from artificial neural network. Artificial neural network, you kind of like needs to put pixel in each of the neuron, right, to represent it. And after that, you like drill deeper. But with CNN, you actually have a feature map that includes already like n numbers of pixels in one time. So it's definitely more efficient compared to NNN for images. Yeah, can you add on, like, Iga, if you have like more thoughts about it?
Yeah, about the Eptanas, or maybe you guys may be familiar with SBMPTN. That's a really beautiful concept. Like why this simple things such doing powerful things in real life. Okay, to now we have tons of questions. Thank you so much. Put them in the chat box down there, and we can move on to the next material because the question is even getting deeper and deeper.
Wow.
Yep. The stage is yours again, Kak Vincent.
All right, thank you so much, Iga. Don't worry about those of you that push questions and then it's not yet answered. I'm going to answer more questions after these presentations. So for the next one, I hope we had a good break, right? For the next one, I'm probably going to spend another like 30 minutes. And after that, we should have like 40 minutes time for Q&A. Okay, with that in mind, let's talk about CNN stacks and fully connected layers, right? And the idea here is that how can we generate real results of the feature maps? And yep, there you go, right? So you see all this mumbo jumbo here, right? Fully connected layers, whatever layers as multi-layer perceptrons, and you see like whatever like very complex structures in the down there, right? Regarding inputs until it becomes like outputs, right? So it's actually a little bit of repetitions about like the concepts that we learned earlier, right? So for example, you see here that there's a convolutions. So the convolutions is actually a part where you look into just a window of it and then like you put it into feature maps, right? And then with the feature maps, you have subsampling, right? So if you don't know what subsampling is, it's basically just max pooling or average pooling, right? Mean pooling, for example. Right. And then you have like smaller feature maps, and after that you do another convolutions, right? Within these feature maps, you do another subsampling, right? And by the end of the day, how you get like from feature maps into the verdicts, for example, whether this is a robot or not, or whether this is a cat or dog, is that you will need to squash it, right? And you treat all the squash component, and then you put it into like each individual neuron, right? So each individual feature in feature map, you put it in the neurons, right? Where you just have like one layer. So for example, 5 to 5 feature map will have like 5 times 5, kind of like 25 neurons there. And after that, you can do ANN as it is, right? But in this case, we call it like FCL, which stands for fully connected layer. And by the end of the day, you have outputs here, for example, whether this is a cat or dog. So we will talk about how you can actually come up with the percentage, whether like the machine is sure whether this is a robot or not, or this is cat or dog. Okay, so this is just a little examples about some CNN that I run with cats images, if I'm not wrong, right? And from the top until the bottom, there is a certain thing that you might want to see. So for example, at the one at the top is just like dots. It's just numerous number of dots, which are sort of clustered. But as you go down, right, when you do the max pooling, it becomes more and more like a curve, right? So it becomes like curvy here. It becomes curvy here. At the down here, it becomes like resembles a cat, right? So there's a texture, right? So from the top here, you see just the dots, lines. In the middle, you see a shape, which is a curve. In the bottom, you see structures. So each of the step, it becomes more and more complicated. The shapes becomes more and more nuanced, right? So it becomes like, oh, I can finally see that there is a little resemblance of a cat at the bottom here, right? So that's what convolution does. It just picks that, oh, a curve is important. Therefore, let's tune it up into our feature map and kernels, right? And after that, we have the max pooling. And when you see the max pooling, you know that it's going to be reduced in dimension. So for example, this is 100 here. We reduce it by 50% to become 50. We reduce it by another 50% to become 25, and so on, right? So by the end of the day, you have like very small component that you can actually process relatively quicker, right? So the more layers that there are in CNN, actually it becomes simpler and simpler. But the feature maps that come about it becomes more complex and complex. So that's the cool thing about CNN. And of course, by the end of the day, we want to sort of like come up with the activation functions where we can get the values of the CNN that we train, right? So we do have like softmax activation functions, and we also have sigmoid activation functions, which are most commonly used in the FCL layers. So softmax activation functions causes the probability scores to add up to 1.0. So for example, here we have pictures of cats and horse, right? And I have 3 labels: cat, dog, and horse. So for example, here I forward propagated it, and I found that each of the image have these values by the end of the day. So these values are actually the neuron values at the last layer, right, of the FCL. And after that, I will use softmax functions in order to squash it into probability of 1 altogether. So for example, for cat here, it becomes like 0.71, 0.26, 0.04. So what it means is that the machine is sure, I think this is like 71% is a cat compared to a dog or a horse. Or maybe like if you take a look at the second one, it's even like more sure with a horse, right? So it puts like 98% I'm sure of a horse. Pasti yakin gitu eh. And the third one is like you see there's a horse, right? But the machine is like, I'm not sure whether this is cat or dog, right? So in the third one is a misclassification, right? So that can happen. If you are jelly here, right? If you are really, really paying attention, you know that the first one here doesn't add up to 100%, right? So it's like 1.01, which is like 101%. And you might be asking like, huh? How do you have 101% probability, right? So this is how like artificial neural network works. Basically, they use a sigmoid functions. And when you talk about sigmoid, is that it's always like never 100%. It's always like, I'm kind of, I think I'm super sure that it's cat, dog, and horse, but I can never be so sure, right? So you always use like probability. And when you use probability, you can never get into 100%, right? So that's artificial neural network is just like sigmoid on crack, right? So it's just like a very super complicated sigmoid. So that's why that if you see here, the softmax functions do not add up to 1. And of course, we will we will sort of like summarize what happened just now. Is that, for example, that we have this input image, we put it into input layer at the down here. The first input layer is just trying to understand what shapes it's looking at. And after that, as it goes through into a smaller through subsampling, it becomes more and more sure that, hey, I think this is a cat, I think this is a dog, because there's a curve, there's a sort of like eyes there, right? So it just keep going up, it's going to learn all of these things. But at the end of the day, you have like fully connected layers, and these fully connected layers is where it's going to say, I'm pretty sure it's 70% is a dog, for example, right? So the top layer here is how we are going to get values from our subsampling feature maps. Okay. So now you might ask me like, hey, how do I actually code it out, right? So a very simple way is just to use TensorFlow and Keras. So TensorFlow is just the back end behind like all of those like inner workings, and Keras is basically abstraction layer. But actually moving forward to TensorFlow 3, you don't really need to use Keras anymore, right? So it's really up to you what you use. But basically, if you think of Keras, Keras is just an API on top of TensorFlow where you can just use and create neural networks quickly, right? So it's just like when you drive a car, you don't really need to know how the engine works, but you just need to know, okay, these are the brake, these are the steer, that's all what I need, right? I don't really need to know, okay, what's horsepower is this? I don't really need to know. So Keras help you to use neural network without really understanding what's a neural network. Good and bad. Yeah. But anyway, we use Keras here, so I can, so we definitely can push it into the time, right? Right. So we use the Keras, we imported it, and by the end of the day, we can create these neural network layers, right? In here, you see that we just built a CNN stacks here. So if you notice that the stacks, you know that basically it's convolutions and pooling, and after that you just run it all the time, right? So basically the 3 here stands for RGB, so red, green, and blue. And basically 16, 32, 64 is like sort of like the number of like layer, the numbers of neurons that in a layer, in that layer. And after that, you flatten it. When you flatten it, then you will have a dense layer, right? So dense layer is a layer during the FCL, right? A little bit of like terminology there. But basically, we will have like 512 neurons here. And the last one is where we have the results, right? Which is the number 1 here. So 1 here, it just indicates whether this is a dog or not, right? So I'm pretty sure it's like 80% of dog, right? But I don't have like any other labels, right, for me to look into. So it just, if you see the activation function is sigmoid there, where it just mentioned that I want to find probability of a certain label. Okay. So hopefully this is clear, but basically we have CNN stacks and FCL, right? And FCL is basically you just like treat everything as how you treat in artificial neural network. Then, by the end of the day, you want to compile it. And of course, just like artificial neural network, you also have those of like back propagations, forward propagations, and you optimize it using like Adam, but you can feel free to use others as well, like gradient boost and whatsoever, it's up to you. Loss will be like binary cross entropy for sigmoid, categorical cross entropy for softmax. So the idea is that we want to optimize on the loss, right? We want to have the fewest loss as possible, and we want to have the models to train itself to sort of like keep changing the prior knowledge, which is the kernel, to make sure that it represents the reality, right? So in the feature maps, it represents about what's important. Oh, if there's a cat, then there should be a curve, right? So basically the back and forward propagations will allow the artificial networks to actually learn what a cat looks like in each step, right? So this is a very strong part, right, of CNN. So C will be convolutions, where it talks about what to input. And neural network is that it uses the convolutions, which is the feature map that are produced by convolutions, in order to come up with a new values data structures for each of the neuron to look at. Okay. So hopefully that makes sense. But yeah, think about it as CNN stacks here, fully connected layer here. And after that, you just treat it like any neural networks, right? Which is
Hello? Another mute, maybe from the hardware there. Pardon us for the hardware issue. Then thank you so much, everyone. Keep filling those chat box with a lot of questions. We have lots of burning questions here related to, kernels and CNN tips and tricks to create a layer. Yep, we have some disconnection over here. I think. Okay, no problem. We will wait for Vincent for a bit. And now, keep asking questions over there. Keep asking questions. Okay, wait. I hope all of you can still hear my voice because, yes, it was on mute over there. And yeah, we also encounter some of hardware problem. Okay, welcome
can
back.
you hear me? Sorry
Now
about
we can hear you.
Okay, thank you. I'll share my screen again.
Okay.
Yeah, this always happens whenever you have a demo. So I always make a joke like everything went really, really well during the rehearsal, but during the demo, then something comes.
Something will come, Scott. We need to kind of prepare. Just like we prepare to train our model and fine-tune it. After this, Kak Vincent will tell us more about fine-tuning a model in CNN.
Yep.
Stage is yours.
Thanks for the thanks for the addition, Iga. So let me just continue. Right. So so after that, you train it like how you train a neural network. You just like fit it, right? And this is what you get. And by the end of the day, you will have these results within cats and dogs. And by the end of the day, you will have like this training and validation accuracy and loss, right? So in this case, you notice that the evaluations, the validation accuracy is actually very low compared to the training accuracy. So the blue color is the training and the yellow color is validation. So why is that, right? Well, if you know the answers, please think about it. But since I cannot see the chat, so I'll just say that it's because of overfitting, right? So whenever you see that the accuracies of your neural network of cats and dogs is like, there's a gap here, the training accuracy is always more than the validation accuracies, then you know that it's overfitting because it memorizes too much from the data, right? So it doesn't take the features, but it actually, so basically it just looks into the wrong features because it memorizes that a dog has to be ... right? So if you want to understand more, I just want to highlight this, that there is actually Teachable Machine where you can train rock, paper, scissors. Right. So if you want to understand more about how CNN works and you just want to train it and just get the results of it, you can do it yourself. And there's also a collab if you want to look into CNN. All right. So I'm going to talk about overfitting, right? So just now we have like overfitting problems. So how we are going to fix it. And there are two solutions that I want to mention. So image augmentations and dropouts, right? So these are a little bit of common mistakes table with the solutions. So let me just mention a little bit about it. For example, like test set as a validation set to test the model. By the end of the day, in machine learning, you don't want to use the testing model and use it as testing data sets to use it as validations because it's going to spill over to how your machine learning is going to work, right? So the test data sets, it needs to be completely separate from the machine learning pipeline, right? Training data sets is where you use the data sets to train your model. Validation data sets is what you use to tune your model. And test data sets is what you use to test your model. So the test data sets cannot be mix with how your model is trained and tuned. Okay, so this is a common mistake even for me. And the second thing is that image augmentations. So usually data set is relatively small. You only have like 50 images, right, or 100 images. So what you want to do is that you want to augment it, right? You want to make it into 1,000, for example. But of course, number of data sets, it needs to be, you need to take a look into the business case, right? And finally, over memorizations, overfitting, right? So we can use dropout or maybe hyperparameters like tuning, such as like epochs, layers, neurons, numbers, right? We can reduce it and increase generalizations, right? So the very first thing that in real life that I will try to do is that can we like augment the data, right? Because most of the time overfitting happens because you have too few sample size. And when you have too few sample size and overly complex model, then usually you have overfitting because the model only memorizes all that your data can offer. So what you usually do is that you have this original image, and I can do flip, zoom, crop out, crop in, and whatsoever, right, to produce a certain numbers of images that actually mimics the original image. Right. So what happens is that I can add on image data generator here. So there's actually a library in Garage that you can just use it. So and after that, I put parameters that rescale, rotation, width, shift, range. So all of these, right, it will create those variants that you see at the right, right? So within 3 images, you get like, for example, 5 images from each, so it becomes 15, right? So with that, you have many different kinds of options that you can choose, and it will generate everything for you. And by the end of the day, you will use this as the data, right, that you are using to train your models. Second one is a dropout. So what happened here is that you are shooting all different layers, right? So you drop different layers randomly from each training steps, right? So for example, in this case, we can put like dropout 0.2. So you shoot like 20% of the neurons, and basically just use the neurons, different neurons for each different training steps. So why is this important? It's because that it avoids overfitting. So why does this avoid overfitting? Well, an analogy that I will share for you to understand is that when you go to BCA or bank, right, you will always talk to a different teller, right? You don't like go to the banks and then say, oh, I only want to talk to Ima or Iga. You don't say that, right? You always talk to a different person, right? And they always like rotate the number of clerks and the clerks that actually serve in the bank. And the reasons why, when I ask about it from my friend, is to prevent collusion, right? So if you know like bank heist, right? For example, like like Money Heist in Netflix, right? Which is a Spanish telenovela, right? You don't want the criminals to know too many things, right? And when you talk to the same people every time, usually you'll be able to ask too many things, right? So what happens is that the banks will rotate the clerks, right? Whenever it serves a certain customer. So this is what happens with the dropout. You don't want your neurons to collude to each other to talk and know too much, but you want the neurons to know just enough from each neuron so that they can actually be more creative with their approach, right? So that's how dropout works, and it prevents memorizations, and of course, it increases generalizations in a certain concept. Okay. So this is overfitting solutions dropout. So you see 0.2 here, meaning that we are shooting 20% of the neurons in each training step. So to run this actually is very cheap. If you see the params here, there's actually no parameters that are done in dropout. You just start shooting it. So it's very, very fast. And if you do image annotations and dropout, this is what you will get. You can actually try out from my collabs. But if you see, the graph is much better, right? Okay. So this is a bit comparisons where you see a huge gap, but now the gap becomes narrower. And of course, your prediction accuracy increases. Okay, So I will spend like 15 minutes to talk about this, and after that, Q&A. So it's basically roughly the timing that we are looking for. But the end results that we want to think about, like once we saw the graph earlier, is that how we can improve more. And a technique that is always used in order to improve these models is by using transfer learning, right? And what is transfer learning? Transfer learning is to leverage pre-trained models by experts, right? So basically, why do you need to train a model from the start when you have an expert trained model, right? Can we actually just reuse whatever that they have created for our purpose, right? So that is what transfer learning is trying to do. And of course, if you take a look into the research and you try to compare all different advancements to what each of the individual architecture that the improvements of the image recognitions is that you will find that there is a plethora and there are so many of the architectures that's available, right? So for example, in this case, we see the ImageNet competitions. So basically they have billions of images, right? I think now it's billions. And it was like sort of like hosted by Fei Li, which is like a very prominent official deep learning researcher in Stanford University, if I'm not wrong. And basically, she hosts these competitions where many different kind of teams, including like corporates like Google, look into it and try to train a model on top of it, right? So you see here that we compare it to the human. So the benchmark is human as 5% of errors here. And you see that slowly and slowly in 2015, we have ResNet, which is better than human, right? So in terms of errors, it's actually performing better than humans. Yeah. So of course, the idea is that can we take advantage of all of those like better than humans model, right? And the answer is yes, right? Which is through transfer learning. And it's not complicated. So basically at the bottom here, you see the CNN stacks and fully connected layer that we talk about. Then after that, you will actually change the CNN stacks into 2 lines of codes, right? Which is just creating a sequential model and you add a convolutional base. So the convolutional base are basically imported from the external models, right? So I'm going to talk about that later on. Right. And basically, for example, in Keras, you can import like VGG16, right? So you can import VGG16 here, which is one of the architecture that's popular, right? And if you take a look, the weights are ImageNet, so it comes from the ImageNet weights, right? And include top equals to false. So basically, it will, if you don't include the top, basically you can train an FCL on top of it. So what it means is that you can repurpose it for your own like business case, right? For example, you're trying to identify all furnitures in IKEA, you will say include top equals to false because I'm going to train my own FCL layer. And after that, the input shape is basically the dimensions of the image, which is 150 pixels base and with 3 RGB, right? And if you try to summarize this model, right, you will take a look that the VGC16 params are huge, right? So basically, these are the numbers of parameters inside all the neurons within VGC16 that you need to interact whenever you do back propagations and forward propagations. And when you train on it, it becomes huge, right? It will take hours before you are able to use the advantage of VG16. Right? So what you normally do is that you need to say that we don't want to train on VG16, right? We don't want to change it because it's already trained on top of numerous images. So what you want to do is just change the top layer so that you can like repurpose the neurons, the features, the weights, right? So that you can use it in your use case. So when you put it at trainable false, well, within a moment, you see that, okay, still high here, but the trainable params is way, way better, right? So the total params is 18 millions, but you actually reduce the complexity of this model by 4x, right? So you have like trainable params of 4 million only. This is way better, and this is how you can use transfer learning. So what it means here is that you have a huge model, right? Let me recap. You have a huge model. You freeze. You don't want to change and retrain it again, but you just want to use whatever that they offer, right? But you just change the top, right? You just change the FCL layer so that by the end of the day, it highlights a little bit of like training the top to reach your use case, right? So you can train the top with your data, right? And then you just change the value from the top onwards. So this is way better, and this is how you are able to take advantage of transfer learning. And of course, this is what happens, right? So for example, in the validation accuracy, oh, actually I need to hide this. Sorry, forgot about that. So in validation accuracy is 0.65. And after you use like transfer learning, you see a huge improvement in validation accuracy to 0.9. So this is really, really powerful because you take advantage of the architecture that's trained by experts. At the same time, that is trained on top of hundreds, millions, and even billions of images, right? So you know that, for example, to collect images and data is usually expensive in terms of time and cost. But by using transfer learning, you are able to take advantage into what has been trained in the past, right? So this is very powerful. This is very powerful. All right, so Collab Demonstrations, yeah, feel free to take a look into it. It's all covered there as well. And the explainable ML as well. So you have like drip dim and also like many different kinds of like looking into what's happening in the black box, right? So at the left side is actually the line. For example, how it looks into the guitar. It takes into the subsegment about for each of the layer and then like render it into a new image, right? Of like the subsegments of what the CNN networks is looking at, right? So this is how we can understand machine learning and CNN. And there's actually a huge subsegment about explainable ML, right? And there are always more and more research into like how we look into images and understand, interpret why a certain image and how a certain image looks into, how a certain model looks into images. Okay. So this is one application of the Deep Dream, which is a psychedelic art. So from image, we take a look into the layers. From the layers, we sort of like freeze the weights of the layers, and then we train it on top of the second image. So if you see here, you see that there's a formations of the dog's eyes and noses, right? So this is how the neurons is looking into like, how the model is looking into the neurons, and it seems to mimic a dog, and the dog is sort of like appended on top of this input image. Right. Okay. So I guess that's all about what I want to discuss. I think we still have time for Q&A.
Yep. Thank you so much.
Right.
Well, I think, the slide is still on. Don't forget to reach out to Vincent through his Medium LinkedIn and some survey that he shared.
Yeah.
Well, Kak, actually, since at the very beginning you explained a lot of things about CNN, especially, we have lots of questions which is technicals, and so because we have a lot of questions, we do have a lot of questions. So I do really apologize to all of the viewers. Probably we cannot like address all of the questions one by one, but I'm trying my best here. Okay, so first, we're going to talk a little bit technical. It's about kernels before we move to another perspective of CNN. So Rifki Novandi asked one question, like how do we define the kernel of the prior knowledge size and value for the convolutional? Like it's like maybe is there any rule of thumb or maybe even a formula, a calculation? Like, how do we define the size of a kernel, Kak?
This is very, very interesting. Actually, for the kernels, basically it's the prior knowledge that is being trained by the neural networks. So you don't actually define the kernel because the kernel is basically the prior knowledge of the neural network. You don't want to tell neural network, okay, this is what you need to pay attention to, but you want to tell the neural network, okay, these are the inputs, these are sort of like the labels, and basically try to learn from it, right? So in that case, you might be able to find out a certain different thing that might be different from your biases, right? So you don't actually define the kernels, but what you define is that probably you talk about the input images, you define the structures, right? The complexity of the neural network, and by the end of the day, let them decide what prior knowledge that they need to form based on the input images, right? And of course, you always need to like evaluate whether they are doing correctly, right? So you need to test it out, right? And always like improve it, right? Maybe you need to improve your input images, or maybe you need to improve your model per se. Maybe it's overly complex, right? So by evaluations, you know whether the neural network is actually performing better, worse, overfitting, or underfitting, and based on that, you can always like fix it and understand what size and values will be the optimal. Yeah.
So it really depends on the data, on the situation, and also about the layers. So there is no like rule of thumb. It's the prior knowledge. Yeah. Because well, Kak, we have probably 4 people asking pretty much the same. It's from Juliandri, it's from Felix, from Zul. So we will just pick one, like really represents all of them. How do you, sorry, I will choose the Zul's one because this is more particular. Zul Fauzi asked this one. Is there any certain formula or a mathematical calculation that we can do as a reference to create a CNN layer? So for example, I'm doing my calculation, my data is like this large, and oh yeah, I need 20 layers. And yeah, like, is there a formula for that?
That's a very good question, right? There's actually a starting point formulas, right? Like you can take a look, for example, how many labels. If you have like many labels, right? How many images for an image, for example, right? Or what kind of image that you need to put, right, for that labels. But there is not really there are actually many different kinds of like philosophy regarding how many different CNN layers. But the idea is always very, very simple. Is that when in doubt, always start with a simpler model, right? So the tendency of like beginners, even like for my friends and myself itself, is that we always want to check the Kaggle, find the most complicated models, and then just use it in our use case, right? So
find what best outside.
Yeah, copy paste in Kaggle. Yeah, I mean that could work, but usually what happens is that it will overfitting, and that is not exactly the right approach here, because the thing is that for the prototyping and for the iterations that you make, you need to trial and error. And when you want to trial and error, you need to fail fast. So if you start with the overly complex models with a huge number of neurons, then what happens is that every time you train models, it could take days, right? It could take hours, it could take days. So how you're going to make a very good prototype of it, right? It's much harder. So what I usually do is that if there are like simple kind of use cases, cats and dogs, for example, I will actually just use maybe like a few hundreds and thousands of images if I can get it, use image augmentations. Then after that, I run a very vanilla models, right, which is maybe like 3 layers of like convolutions and max pooling that you saw earlier, right? And after that, I just run it, right? And based on that, evaluate it, understand whether it's too complex or not. If it's too complex, then of course, if it's too complex, maybe overfitting, right? So maybe you need to add on more images. But if it's like underfitting, right, then you can add more layers. And by the end of the day, if I stay stuck, then I can use transfer learning. So usually that's what happens.
Well, that's our daily life as a machine learning engineer as well.
Yeah, but there are so many ideas on how to find challenges. I think you can just Google it, you find a few hundreds more.
Yeah, it's like it's a form of art, I guess. So yeah, picking like the best model between here and there is really good practice also. Well, speaking of overfitting, there is like one unique question from Fajar. He asked why we set dropout layers instead of tuning the number of neuron itself. So okay, we know dropouts, we randomly kicked out some neurons, but why don't just like really decrease the number of neurons that we have inside of our dense layer, for example? Like, what is the technical advantage to have a dropout instead of simply decreasing the layers?
That's a very great observation, I think, and I think it's a very good question because like it encourages us to think right about one approach to the others. And a funnier way on how to look at this, the simplest way is that if you know like how sigmoid works, is that it's based on Bayesian theorem, right? And when you talk about Bayesian theorem, it's always like depends on a certain reference, right? You use like prior knowledge in the Bayesian, right? And the idea of the dropout is that it sort of like reduces the chance of not optimal information gain, right? So if that's the case, right, the dropout is actually working really, really well because it limits your information gain to be the most optimally as possible, right? By taking a random sampling of which neuron to activate for each layer, right? So in terms of like Bayesian, if you know Bayesian, which is like probabilistic kind of like conditions, right, to identify the outcomes.
We're going to speak about that in Bangkit. Like in the next lessons in Bangkit. We're going to talk about Bayesian.
Definitely. So definitely the dropout actually takes advantage into that. So the idea is that you want to optimize the information gain, right? You don't want it to be saturated from the start, right? So dropout actually takes care of that. But of course, regarding the number of layers, number of neurons in each layers, that could also be like tuned into it. So if you know Keras, there's actually a Keras tuning library that you can take advantage into it. But of course, in most cases, I actually want to suggest dropout first because it's very simple. It's basically like almost costless. There's no cost in just like adding dropout. And by the end of the day, I think you get the big bang for bucks. Whereas for hyperparameter tuning, usually it takes more time to keep running and experimenting over more models. Yep.
Okay. So still speaking about the dropout thing, Azrael also asked an interesting question. So you always can relate to this one as an ML engineer, especially working in deep learning. Our dropouts is like how can I say, like one of the major solution to decrease the accuracy due to overfitting. In the graph it tells, so it will get better result but decrease it. I mean like better, so like the validation and like the train is not really far away, so it really cures the overfitting. But most of the time, if you tend to use, we do the dropouts in the layer, it tends to decrease the accuracy. So how can we come up with this dilemma?
That's a very interesting observation as well.
That's my own problem as well.
That's a very interesting observation. So how do you actually get into the dilemma? Honestly, I think it's a bit straightforward. Usually, I'll just use dropout whenever I see an overfitting. Usually, that's a solution. A machine learning engineer life is like trial and error, right? So you honestly, I will have to say I will never know if I never try it, and the easiest way to try is that dropout, right? So it's a fail fast, right? But the idea is that whenever you see overfitting, it's always good to make your models less complex, right? Because the more complex a model is, the more likelihood that it will just memorize everything, right? Because it thinks too much, right? It's just like how we cannot sleep because we think too much of an exam tomorrow, SKS, right? But but basically, you want to reduce SKS, and basically, a dropout is a way to say that, hey, you don't need to really learn word by word, but you just need to highlight what's important. And if you just like throw a dice and then just like read like many different kind of pages, maybe in different sequences, then there's a likelihood that it will make sense to you by the end of the day, right? So, so it's actually sort of like learning tactic that I sometimes also use for to practice for exam.
Yes, so really balanced. So it's really like flight time. It's really like jam terbang, like so, yeah, to come up with dilemma, I guess.
Yeah. So you kind of like mix everything. Like for example, like during my math exams, I don't want to just learn all factorizations within like 50 question of factorizations in like persiapan ujian. But I also want to mix, right? Maybe like the first question I want factorizations, the second question I want like maybe like geometry, the third section I want to do something else, right? So the dropout kind of mixes all of those, right? So to optimally make sure that you understand stuff.
Yes, to reduce like the overfitting inside of our brain, I guess.
Yeah, exactly.
Okay. Now this question a little bit shifted to like the model building. Kak, you also mentioned that we tend to use simpler models and let's say lesser dense network. So Vincent has just started learning TensorFlow there, and then Vincent asked this one on TensorFlow. Yeah, on that TensorFlow, we're talking about TensorFlow, not directly on Keras. Why we use lesser neural? I mean, like we start small, like 16, 30 to 64. Why don't we like start like maybe 2020, for example, 2048 layers in the first layers? Like why we tend to begin with such a small number and then we kind of increase them and then we can decrease them maybe like to the end of the deciding layer? Why we tend to do that? Like
Yep.
yeah.
I think it's a very nice question. Like the first thing I recognize is that you have the same name as me. So, yeah.
Okay, so Vincent Austin.
Vincent, yes.
Okay.
Yeah, but you have the I think cooler name than me. Okay.
Vincent Charles. Okay.
So yeah, so to answer your question, Vincent, is that why we use something that's simpler, right? At the start, why not just use big numbers? It's because again, the idea is that you want to sort of like step by step, right? To fail fast, right? You want to like iterate through your trial and error process. And the easiest way of this is like to make sure that you start small, and after that you keep like using whatever that you evaluate to hyper tune it. Like you can after that like build a tougher and complex models, right? So the idea is that it's like how we learn math, right? For example, like when we want to learn multiplications, we need to understand the concept behind additions, right? So we start with addition first. We know like 5 plus 5 equals to 10, right? And then after that, we know that 5 plus 5 is actually 5 times 2, right? And you just summations it and then like implement like additions multiple times to become multiplications. So the idea is that you want to fail fast with something simpler first to reduce your efforts of like training it and also trial and error. And by the end of the day, you always want to tune it to something that resembles the perfect fit. So it's not underfit nor overfit. So that's why we need to start with the smaller numbers if possible.
Oh yeah, so we always want to try simple because it's obviously faster.
Yeah.
Well, like for example, my model behind me, it's my model for thesis. It's also CNN based, and it takes 2 weeks to train. So this big boy is pretty much complex. Speaking of it's complex. So
Nice
start
way
small.
to
It's really good.
demonstrate.
Okay, speaking of like start small and simple, and you also ask about so many like biological perspective of the CNN and artificial neural network in general. So Kiagus Muhammad Arshad asked this question. The another analogy about CNN, it is same like anatomy in biology that you just said. I mean like it is the convolution is like the 0 and 1 to determine this convolution. sorry, it's a little bit difficult to tell. Okay, let me repeat this thing. The another analogy about CNN, it is the same like anatomy in biology that you just said. And it's always use 0 and 1 to determine the convolution, because not only black, white of the colors. I mean, like maybe how's the case maybe with like a more, we were speaking outside of the bitwise, maybe like a deeper,
Yeah.
how can I say, like the deeper color, like you have the RGB, and then we have like 0 to 255 as a value. Like, well, we can translate that to, how can I say, the 0 and 1 part. We can translate it, oh yeah, it's pretty much like our nerves. But how about outside of it, or maybe values in between? Can we still make a good analogy of that in terms of biology? Because I'm doing that all the time.
Yeah,
Yes.
that's a very nice question for Arshad, right? Yeah, so let me try to understand what you're mentioning. I think there are like a little bit of a few questions here. But the first question is that whether it's the same as anatomy in biology. I believe it is, right? Like how I mentioned to you about CNNs, like convolutions, where we like sort of like skim through an image and then try what's important for us with for example, the example of young lady and old lady, right? So that actually you're using your prior knowledge to identify a certain label, whether it's young lady or old lady. So it's definitely similar to biology. Artificial neural network itself is definitely mimicking like our anatomy, which is like God's created organs, right? and I think it's really good. Like we can glorify God by learning CNN.
Oh yeah,
Yeah.
we do it a lot.
Definitely, right? Whenever I learn machine learning, I feel that it becomes more and more like how our body works. Yeah, and of course, whether like we need to use 0 and 1, it's actually not necessarily the case. For example, in the examples that you saw regarding the images, and even if you take a look at the collab that I used, sometimes you deal with sort of like in between, like for example, 1 to 2, or you deal with RGB, so you have like sort of like 1 to 2, 1 to 2, 1 to 2, something like that, or 60, 60, 60, which if I'm not wrong, it's like sort of like a purplish color, if I'm not wrong. Feel free to let me know. So you can actually do that and have the neural network look into the images and then figure out whether this is something important or not. And how it knows it's important or not is that by keep updating the kernels, updating the prior knowledge. And how it updates the prior knowledge is that you know through the neural network stuff, which is the back propagations, where it's trying to change their weights, right? So in this case, in CNN, we always synonymous weights as kernels, right? Because the weights is actually keep updating as the kernel keeps updating every time it back propagates. So every training step, right? So yes, it is like anatomy in biology, and yes, we can have a more nuanced kind of numbers like something in between 0 to 255.
Okay, so it really is inspired by nature, I think. Yeah. Okay. We have also lots of questions asking about how to start. I mean, like for example, we have Rizky here ask for a little bit tips. What is the good way for beginner to learn how to use CNN and how CNN works? Does it a good one if we directly go to Keras and we import Keras like directly, for example, or maybe another approach? For example, we can do some mathematical approach first. But here I want your point of view, Kak. I mean, like, how did you learn CNN in the first place? Like, in your opinion of good practice? Yes.
Yeah, that's a very good question. So how does a beginner learn CNN, right? So looking from my experience, I actually didn't know about machine learning much. I used to be a software engineer rather than machine learning engineer, right? So I only learned CNN like 2019, right? So
whoa,
it's
so early.
it's just, and I'm still considered like what's CNN? I thought it's a news station, something like that, right? Like something like RCTI. No, it's not like that. But But basically, how I learn CNN is basically through my work because I deal a lot with images, and it's just nice that whenever you talk about website bodong and how people get tricked with it, it's usually because the eyes, right? So the eyes see first, right? And the eyes will trick you. So you know that this is like bodong is like Facebook, but it's not Facebook. Only when you dig deeper into the URLs or maybe other features that that it looks at. But why you get tricked is because visually it looks like Facebook. So that's how I use like this kind of like machine learning. I use like image embedding and I use like image recognitions, kind of like models, right? And I try to keep like experimenting on it. So that's how I actually learn because there's a use case. But if you want to know like how I actually learn it, I have like multiple sources. For example, like Bangkit is definitely one of them. Yeah. Bangkit definitely there are some CNN courses, and I think I also like bring up to you about CNN works. And the second thing is to get your hands dirty. So just go through to some practices, try to use it in your real life. If possible, create a simple applications. For example, like I think the previous one I mentored like Bachara, right, which is like sort of like using like hand signals, right? I think you know about it. Yeah, using hand signals in order to help people that are disabled. So they definitely use like image recognition a lot, and there's so many frameworks out there, not only in CNN but also within like YOLO. You have like SSD, right, single shot detector, and you have like many different kinds of like models out there. Okay, second question. Yeah, sorry. You have like.
Okay. Yeah, we still have time. Speaking of, once again, model, and we also discussed a bit about another model outside CNN that really good on images, just like YOLO, the SSD, or maybe like residual network, the ResNet. One of my friend asked, Arya Winata asked this, and some people also ask this, but it's pretty much general question. How we are able to determine pre-trained model that's suitable for our application? Any tips, any rule of thumb, or what to look up first?
Sorry, I don't really get the questions. Can you like put it?
Okay, I'll repeat this one.
Yep.
How are we able to determine which pre-trained model is suitable for us?
Okay, that's very that's very good question, Arya, right? And thanks a lot, Igor, for reading this, right? So how do we know which pretend model is suitable for us? Any tips, maybe? Yeah, that is actually very complicated, right? Honestly, the answers of how we know it's suitable is depends. But I give you a little bit of guideline from my own experience, especially at Google, is that not all pre-trained models breed the same, right? So for example, use cases, right? Some pre-trained models are built on top of like landmarks, for example. So there's actually a model by Google that's called Delph, right? So they actually just train on top of landmarks like Monas or like Tower of something, right? Or like Candi Borobudur. So they talk about landmarks, right? And obviously they use it in Google Maps and whatsoever, right? And some other models are actually trained on top of like furnitures, right? So there are actually some models that pre-trained on furnitures, right? Like for Airbnb usage or maybe for IKEA usage, right? Right. So the thing is that it really depends on like what kind of use cases you have, whether your model is like, let's say that you are trying to identify furnitures or you are trying to identify cats and dogs, right? There are many different kind of models, but a simple guideline is that you need to take a look into three things. So the first one is size, right? So obviously you don't need a complex models if you just have like one label or maybe just two labels. You will need a more complex model if you have more labels, right? Yeah.
Exactly.
So obviously that's one thing. And the second thing is definitely what it is trained on. So like what I mentioned is like furnitures or landmarks, right? It will actually determine the usefulness, right, in the future. And the third one is actually the memory, right? The kind of course it relates to the complexity, right? So for example, if I train FijiG 19, right, every time you open your Android phone, then you will complain to me, right? Because how come my battery died so fast, right? Died so fast because of the Android, right? Then all of you will change to Apple, for example. We don't know, right? So, so all of these needs to take into account. And also, of course, there are speed involved as well. So, for example, why we use YOLO in videos compared to STNN is because that it's doing single shot, right? Then after it detects it, that's why it's called like single shot detector, and it's very, very fast, right? If that's the case, because you just look into it and then you estimate directly. So there's always a trade-off between accuracy and speed, right? And that's what we want to take a look into every pre-trained models.
Okay, that was really scope, and accidentally just gave us a really good rule of thumb to choose a pre-trained model there. Yeah, so once again, if we want to make, for example, we create our vanilla model and then, or maybe we have a pre-trained and then we modified it, make sure that we have a good documentation. That's what we trained on, and then like the transfer, that will increase the transferability, because Michael asked me, but you already answered Michael's question also, like in the explanation. So yeah, that's a really good one. Like one stone with two birds. Really good. Okay, moving on to evaluating CNN models. A lot of people also ask about evaluation. An-Nur asked a very simple one. What is more important, accuracy or recall, or even both, like F1 score? What do you think?
Okay. Yeah, that's actually one thing that people talk to me about, like how to evaluate. And I laugh because like this is basically what I've been dealing in every machine model that I train, right? Oops, I think there's a problem with Iga's video. Okay, while we are waiting for Iga's video to turn on, let me try to answer like how do we evaluate it? Okay, so first of all, when we talk about like precisions, recall, and F1, you need to understand your problem, right? So basically, you're dealing with classification model. So spam or ham is definitely one of them, or maybe like you try to take a look into like Gojek scam, for example. Then you look into like a lot of features, and try, and maybe you have like a simple models like decision learning, decision tree models, and after that you come up with the convolution models, and then you have like precision, recall, and F1, right? So how do you use precision, recall, and F1? Sorry, Iga, I just mentioning like how you use precision, recall, and F1, right? So normally, for everything that is very sensitive with positive, right, with how the models is accurate, you need to take a look into precisions. For example, like for health, right? If let's say whether like you are talking about cancers or whatever, then you need to have very high precisions. If not, then it will be a false signal, and I think people will sue the hospital, right? And recall is that where you need to know, like, okay, what are the kind of accuracy is not really important, but what I want to know is that which are like potentially having a certain positive situations. So a very good way to summarize precision recall is like how I mentioned about COVID, right? So for example, we have PCR, we have swab tests, we have antigen, right? So antigen is very recall focused, basically of like how many number of people, we just care about the cost, and we just care about like whether a certain person sort of like have a certain antigen, right? Which is not that accurate, but we still use it because the recall is high, right? It's able, out of like all COVID people out there, there's a high likelihood maybe we take one or two of them, right? So that's recall. But when you talk about like whether this person really has COVID, right? Then we talk about PCR, right? Because people need to take PCR like whenever they want to fly, for example, to a country that's really strict. Then they were like, okay, you definitely cannot have COVID, right? So you need to have it lab check, right? So that's where like precision comes in. So PCR is like for precision, and swab test is for recall, because you just want to spread the net as much as possible.
Okay, so it really is like
exactly
the implementation. Like I'm as a student, I learn in university. Oh yes, in medical implementation, you need to, for example, make precision as number one, or in this application, you need recall and so on. Like there's in universities, there are some rule of thumbs. Oh yeah, medicine, like recall, for example. But it's not always the case, right? We are
It's
talking
not
the
always the
same,
case.
the COVID case, which is medical, but sometimes we need to make a head recall out of precision, or even the opposite. We need to make a head precisions. Wow, that
Yeah.
was insightful.
Yeah, so the idea is that like when you have a swab test, right, maybe you just spread the net as much as possible. And if you find a few other people, right, then you might want to decide whether they are quarantined or not. So they need to take PCR, right? So usually in medical, those can be interchangeable, right? So you can sort of like lay on top of each other and it just makes everything more certain, right? So that's definitely one of them. For F1, it's basically just harmonic functions of precision recall. So usually you just use it if you're not sure which to use.
I'm always using F1 score, to be honest, because I'm not sure between precision or recall in most cases. And
Yeah.
speaking of my camera fall down there, and I need to switch to this camera, which is recorded. Well, CNN also going to face that kind of similar situation when the camera is not so good, where the camera quality is maybe decreased or maybe just accidentally dropped, just like my camera there. So Farza asks, and maybe I will ask the same question because my camera just dropped. Can CNN identify object in an extreme angle, an acute angle, like in a very strange shape? For example, can it like detect whether there is a dog or a cat when the dog is maybe upside down, or maybe like extreme cases?
Yeah, that's a very good question. Can CNN identify object in extreme angle? And the answer is, actually, I want to say it depends, right? It depends on the input image that you put.
Everything is depends on the data, I guess.
Yeah. Which is why the image augmentation is come in, right? Because image augmentation is trying to simulate all of these extreme angles, right? And sometimes it's not the complete images, right? So for example, maybe you can take only the half side, right? Only the right side of my eyes, and then onwards, and then you can determine whether I'm human or robot, right? So image augmentation is trying to teach the model that actually some images at the extreme angles, it could still be labeled as a dog, right? So the idea is that like just give them as much like representative samples as possible. If let's say that you imagine that you will have a lot of like acute angles, then give a lot of like input samples that have acute angles. As simple as that, and hope that your models will learn about it and definitely catch it at the moment you test it, right?
Yes. That's definitely. Once again, the answer is augmentation. And also speaking about augmentation, Rexy asked this. Should we use non-proportional scaling in image augmentation? So non-proportional scaling is like really make it too wide or make it too tall or maybe zoom it like way too big or too small there. So do we need that kind of augmentation? And does it affect the model ability to identify images in validation set, which are obviously not augmented?
All right, so this is a very nice applications of like image augmentations, exactly. So thanks a lot, Rexy, for bringing it up. So you can do non-proportional scaling as well in image augmentation. So why non-proportional scaling? I sort of like imagine that you sort of like zoom in proportionately within the y-axis and the x-axis. So that's how I define it. Maybe if you have different definitions, let me know. So it's sort of like like you take a look into a very old TV and it just like squint it, right? So from a very wide angle, very wide dimensions to become a very squint dimensions. So image augmentations can be used for that as well, right? So it can zoom in, zoom out. It can be zoomed in a non-proportional scales. It's no problem, right? So you can just like I think it has. I can't remember the parameters, but it has a parameter to do that in the image generations function. And then does it affect the model ability to identify images in validation set which are not augmented? So the idea is that for the validation sets, it needs to have like a certain sort of like representations that your training set has, right? And the idea is that like if your validation sets like is actually not augmented, then what happens is that it's going to be tuned based on non-augmented images, right? So even though it's trained with augmented images, right, but it's not validated with it's not tuned with augmented images. So it will actually bring a bit of skew, right? When you are testing it, it might not be performed as nice, with as nice as the case like you have like augmented for everything, right? So train, test, validation.
Yep, just make it proportional, make it, yeah. So yeah, it's okay to use non-proportional scaling, but make sure that we also have a proportional split of data. I think that's like the whole answer.
Exactly. Yeah.
Speaking of augmentation and data, Vincent also asked, another Vincent asked, what if we use too many augmentation instead of our training data set? Like, is that going to be effective, especially in the real case use?
If we use many augmented images, will it be effective? That's a very good question, Vincent. And the answer is that it really depends, right? So it really depends on the whether your data is representative or not. So for example, right, let's say dog, right? If let's say I only have one type of dog, which is just the black dog, right? And then I image augment it, right? It will never solve the problem of a dog with red color or with brown color. It will never solve the problem with that, right? Yeah, it will just be unsure whenever it sees the brown dog, for example, that has like completely different features, completely different curve, completely different patterns and textures about what dog is. For example, like bulldog, right? Bulldog is completely a different breed compared to like the other dogs. Like it's very short, it's very fat, but if you just correct. And if you just train on top of like let's say like Hachiko or like those are very cute dogs, right? And then you try to test it with bulldogs, no matter how many image augmentation you have, it will never work, right? Okay. So it's definitely the idea there.
That's the case. We have maybe tons of data, and then we can do tons of augmentation. What if the opposite, Kak? Firdaus Maulana asked this. Why do we get an input ran out of data warning when training the data, and how to solve it? And maybe you have an experience working with small amount of data inside of deep learning.
All right, thank you. How do we get an input ran out of data warning when training data? I'm not really sure about this warning actually. Are you familiar with this warning?
I'm not quite familiar, but I'm assuming that like the batch is like too big for too small amount of data.
Yeah. So usually it doesn't get a warning. It doesn't get an error. Probably it's a warning. I think in TensorFlow, it might happen. So when that happens, is that there is maybe a statistical validations before running the data into the model. So what happens is that if you take a look into ML ops, right, which is machine learning operations, and if you use like TFX, TensorFlow Extended, or maybe like any other stuff that talks about ML pipelines and how you retrain it, making sure the data is schema is right and the statistics is right. So usually before putting into the model training, there are some steps that are required for statistical validations. And the statistical validation basically will give that input is not representative, kind of like warnings, right? So I'm imagining that could be something like it, but let me know if I'm wrong. But usually when that happens, that is because there's no variance. There's not much variance into the input data. For example, like it can do a color histogram, which is a very quick operations, and it checks that the distribution of the colors is almost the same for each of the image. So they, for example, you can use like statistical validation that's called sum rank, right? So it's actually a concept that checks whether distribution A is similar to distribution B or not, right? And if it's too similar, basically your data is not representative and you need to check your data again, right? So in the statistical validations, it will give this kind of like warning. So if this warning happens, then you need to add on different kind of images that the color histograms distributions would be like a lot more varied, right? So the variance is very, very effective when you want to see how similar how homogeneous the input data is, and the ideal case is that you want it to be heterogeneous as well. Yeah.
Yeah, to increase the, let's say, the statistical difference between both of the data and both of the class as well. Yes. Okay, last but not least, this question may be a little bit different from what we're speaking. We're talking a lot of technical, but now it's more of like the part of the job. So Kenneth asked me, and I know you can answer it in a very good way. What are the different things that makes ML ops different than the DevOps? This is a
Yeah.
heart-rending question, Kak.
Thanks a lot, Iga. I think this is a very great question because just recently I did a presentation about ML ops, like outside Google as well, outside Bangkit. So I'm very familiar with it. I actually did one about ML ops as well in the past for Bangkit. So this is something that's really close to my heart. So the idea of DevOps is that it looks into the technical aspects of operationalizing things, right? So DevOps come about because like in the past, everyone's still in the waterfall kind of process. Like it's very, very slow to make some features changes. It's very, very slow to follow what the customer needs or the user needs. So DevOps is actually a sort of like movement.
Okay. The Bluetooth headset is went down again, I guess. Okay. So this is a very beautiful question also, Kenneth. The difference thing between ML ops and DevOps. While we are waiting for Vincent to join us back, just gonna tell my experience about the ML ops and DevOps. So here, at least in my laboratory, we have like kind of two people. Also, we have ML ops. We have like the ML guy, just the ML guy. So the ML guy really focuses on how can we build the best model with the best accuracy or best recall or best, you name it. But the ML ops really just try to deploy and make things happens. Okay, go back to Kevin.
Yeah. Let me try to summarize it. So basically, thanks a lot, Igor, for covering me. Basically, DevOps is like so basically you want to make features changes fast, right? And you want to develop faster, right? So that's why there's a DevOps things, which is like CI and CD, continuous integration, continuous development. And what it works is that it works in an agile way, right? Where you have like rather than waterfall, it's very iterative process of like requirements, development, testing, and of course launching it. Right. So DevOps is built for the technical aspects, right? So you might think that DevOps really works in game development or really works in software development. But what if you put in data, right? So when you put in data, then it becomes more complex. Why? It's because that let's say you're playing like PS1 10 years ago, and you play PS1 today, Legend of Zelda or like I know like Mario Kart, right? It still works. It's still going to work same today, right? Compared to 15 years ago. But let's say that let's talk about Gojek, right? So does Gojek work the same way 5 years ago compared to today? No, it's going to be very different because the data changes as well, right? And when the data changes, the model changes. When the model changes, the behavior changes. So MLOps recognize that there's going to be a data and behavioral changes, right? And because of that, it tries to do a bunch of statistical validations, and it tries to do a bunch of like other operations outside DevOps that dealt with the operationalization of data, right? So by the end of the day, you can launch machine learning models that are reliable, that could be used in a stable manner, and that can be fast as well. Yeah, so that's how DevOps and MLOps is different.
So okay, that's also telling us about the importance of ML ops here. Okay, that's all the question. That's a wrap. Thank you so much, and we do apologize because we cannot answer all of your questions, people. Because yeah, the questions are really hypes here for this session. Thank you so much, Vincent and Tatan, for joining us in the middle of the night there in the United States, and say my hi to fellow Googlers out there.
Yep. Thank you, Ika. I will say hi to fellow Googlers.
And thank you so much for all of you have been tuned out. Like 400 of you Bangkit students have been tuned out from the beginning till the end of the session. Thank you so much for once again joining us. And don't forget to fill the attendance down below. It's in a comment section. Yeah, we do YouTuber things, guys. No. Yeah, don't forget to like, ring the bell for the next non-mandatory sessions. And here I'm Iga Narendra and Vincent Tatan here. Once again, really want to thank all of you. And if you still want to reach us after the session, you can always reach Vincent through LinkedIn, leave him a message, send him an email, tell tell them, Kak, your at Google email. Come on.
Sure. My Google is Vintatan, Vintatan @google.com. So feel free to reach out to me, but please don't spam me. If you want to spam me, then please put it on LinkedIn.
Yes, don't spam him because he created an algorithm to distinguish spams and real emails. This is the security part of Google. Okay, thank you so much. And well, you know if you want to reach me. And see you guys in the next session. See ya, and good afternoon, everyone.
Good afternoon. Bye bye.